Hello friends, I welcome you in lecture number 4 on series solutions of differential equations. From this lecture onwards, we are going to discuss that how to find out power series solution of a given differential equation, and that method is called power series method. We have discussed about ordinary and singular points, so our power series method will be different if we are interested in the power series solution about ordinary point, and if we are interested about regular singular point. We are familiar with these two definitions, ordinary and regular singular points. So we have two methods for power series solutions. If our equation is y double dash plus px into y dash plus qx into y equal to 0, and if x0 is ordinary point of this differential equation, then the method for finding power series solution is different from the method of finding power series solution about regular singular point. So first we will discuss about ordinary point. First we will discuss that how to obtain series solution near ordinary point, and after completing that method we will discuss that how to obtain power series solution about regular singular point. So in this lecture our focus will be on the power series method if x0 is an ordinary point. Now what is power series method? So we have one result or theorem which says that suppose x0 is an ordinary point of this differential equation y double dash plus px into y dash plus qx into y equal to 0. Suppose x0 is ordinary point of this differential equation. That means this px and qx are both analytic at x0. Then that result or theorem says that if x0 is an ordinary point of this type of differential equation, then this differential equation has power series solution in this form: sigma an times x minus x0 raised to n equal to 0 to infinity. If x0 is ordinary point, then power series solution will be always in this form. Now this is linear differential equation of second order, so its general solution will look like this: some constant, say c1 into y1 plus some another constant c2 into y2. So this y1 and y2 will be in this form: y1 equal to series solution in powers of x minus x0. Similarly y2 will be some another series in powers of x minus x0. So remember this result, that if x0 is ordinary point of this equation number 1, then it always has two linearly independent non-zero power series solutions. And once we know that solution is in this form, we can put that solution in equation number 1 and we can decide this unknown constants an. So idea of power series method is based on this result. So whenever we want to find out power series solution of this type of differential equation, then if x0 is ordinary point, then we will start by considering y equal to sigma an x minus x0 raised to n. We will assume that suppose y equal to sigma an x minus x0 raised to n equal to 0 to infinity is solution of this equation number 1. So if this y is solution of equation 1, then we can substitute value of y in this equation. So if we write this by expanding, for n equal to 0 we have a0, x minus x0 raised to 0, that is 1, plus a1 times x minus x0 plus a2 times x minus x0 square plus a3 times x minus x0 raised to 3. Now this x0 is known to us. It will be given in the examination that find out power series solution about this ordinary point or about given point x0. So x0 is known to us. What is unknown for us is all these coefficients a0, a1, a2, a3. We don't know what are these coefficients an. So our aim is to decide these coefficients an. So for that we first write in this form, and if we find out first derivative, then we will have y dash equal to derivative of a0 is 0 plus a1 derivative of x is 1, derivative of x0 is 0 because it is a fixed real number, plus derivative of this term is a2 constant, derivative of square of x minus x0 is 2 times x minus x0 raised to 1, plus a3 constant, derivative of cube of x minus x0 is 3 times x minus x0 square, and so on. And this we can write in sigma notation as y dash equal to, here we can see if I have 2 here, suffix of a is 2 and suffix power of x minus x0 is 1. Similarly, if I have 3 here, in suffix I have 3, and here power is less than 1 by 3. So we can rewrite in this way, n times an x minus x0, and here this is n, so I have to write n minus 1 here. That means I can write y dash in terms of sigma notation as y dash equal to sigma n equal to 1 to infinity n times an x minus x0 raised to n minus 1. So we can write directly also from this term. If we differentiate this quantity, then I have an constant, and derivative of x minus x0 raised to n is n times x minus x0 raised to n minus 1. But instead of n equal to 0, summation will start from n equal to 1 to infinity. So this is y dash, and we will require y double dash also. So similarly we can write that y double dash is equal to sigma, this quantity is constant n into an, derivative of this is n minus 1 times x minus x0 raised to n minus 1 minus 1, that is n minus 2, and instead of n equal to 1 to infinity, we will have n equal to 2 to infinity, and this I can rewrite as n times n minus 1 times an times x minus x0 raised to n minus 2. So this is y double dash. So we will require y dash and y double dash, and we can easily remember, if y is sigma n equal to 0 to infinity an times x minus x0 raised to n, then y dash is n times an x minus x0 raised to n minus 1. This term is nothing but derivative of this term. The only change is we have to start from, if I have n equal to 0 to infinity here, I am starting from 1 to infinity here, and here I am starting from 2 to infinity, and I take derivative of this n into an constant, derivative of x minus x0 raised to n minus 1 is n minus 1 times x minus x0 raised to n minus 2. So these are the values of y, y dash and y double dash, and we know that y is solution of this equation. Therefore we can put values of y, y dash and y double dash in this equation. After that we can compare the coefficients of like powers of x on both sides. We will have this type of things. We will try to write this left hand side in this form a0 plus a1 times x minus x0, a2 times x minus x0 square, and so on, equal to 0, so that all these coefficients of this left hand side must be equated to 0. So here, after putting values of y, y dash and y double dash, we will be able to decide the coefficients of different powers of x, and we will equate those coefficients to 0. And once we decide these coefficients, we will put their values in this solution which we have assumed from the very first step, and we will be able to decide the power series solution. So this is the idea of the power series method. I have written all these things here. We are discussing series solutions near an ordinary point. We consider second order linear ordinary differential equation y double dash plus pxy dash plus qxy equal to 0. If x equal to x0 is an ordinary point of equation 1, then equation 1 has two non-trivial means they are different from 0 solution, linearly independent power series solutions of the form y equal to sigma an x minus x0 raised to n, and then we will find out y dash. Y dash will be sigma n equal to 1 to infinity, and we differentiate this, and we have n into an times x minus x0 raised to n minus 1, and y double dash will be sigma n equal to 2 to infinity n minus 1 an x minus x0 raised to n minus 2. So this we will write directly when we are solving the differential equation, and we will take care that here n starts from 0 to infinity, in y dash it is from 1 to infinity, in y double dash it is from 2 to infinity, and then we substitute all these values of y, y dash and y double dash in equation 1, and then by comparing the coefficients of same powers of x from both sides, we will be able to decide these unknown coefficients an, and then we will be able to decide our power series solution. So this is the idea of the power series solution when we are finding power series solution near ordinary point. So this is all about this session. In next lecture we will discuss one differential equation, and we will see how to obtain power series solution of that differential equation. Thanks for